Deterministic and non-deterministic finite automata recognize the same class of languages. This equality might be surprising because NFAs appear to have much more power than a regular DFA. This also might be surprising because designing finite automata to recognize a particular language might be much easier with an NFA. Now, in order to prove this equality, we have to be able to convert any NFA into a DFA. Let's do this with an example machine with 3 different states. This machine features an epsilon transition and multiple transitions from a single state. The big question is, how can we simulate a machine being in multiple states at once in a DFA? Well, we start by generating all possible state combinations for a given NFA. The total number of possible states is 2 raised to the power of k, where k is the number of states. This includes the empty state. For this machine, we will have 8 total combinations: 0, 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3, and the empty set. First, let's mark our start state. We do this by finding our original start state and taking it along with any states that result from an epsilon transition as part of our start state. So in this case, 1 is our start state, but it has an epsilon transition to state 3, which means that the combination of the 2, state 1, 3, becomes our start state. Next, let's mark our accept states. These include any state that contain the accept state from the original NFA. So here, any state with a 1 will be marked as an accept state. Next, we consider each of these new states and follow their combined transitions given an input. The empty state is easy. It will stay put given any input from our language. Now look at state 1. In the NFA, there is no output arrow given an input of A, so we transition to the empty state. Given an input of B, state 1 will transition to state 2. State 2, when given an input of A, travels to both 2 and to state 3. So we combine those 2 transitions into a single transition to state 2, 3. When state 2 receives an input of B, we travel to state 3. For state 3, an input of A will take us to state 1. But take note that this also has an epsilon transition back to state 3. So we combine those 2 transitions and go to state 1, 3. With an input of B, state 3 will go to the empty set. Now we look at the combination states. 1, 2, when given an input of A, will travel nowhere from state 1. But going from state 2 with an input of A will stay in state 2 and transition to state 3. So we go to 2, 3. In state 1, 2, when we receive a B, state 1 will travel to state 2, and state 2 will travel to state 3. So we add our B input to the arrow that we already created going to state 2, 3. Next is state 2, 3. When given an input of A, state 2 will go to both state 2 and state 3. When state 3 is given an A, we go to state 1. We also go back to state 3 because of the epsilon transition. So on an A, we end up in state 1, 2, 3. And when given an input of B, state 2 will travel to state 3, and state 3 has no transitions triggered by B, so we will transition to state 3. Next, let's look at state 1, 3. When given an input of A, state 1 will go nowhere, and state 3 will go to state 1, which by epsilon will also go to state 3. So we continue in state 1, 3. When given an input of B, state 1 goes to state 2, and state 3 goes nowhere. So we will transition from 1, 3 to state 2 given B. Last but not least is state 1, 2, 3. Let's examine where each one of the component states go given an input of A. State 1 goes nowhere, state 2 goes to state 2, and state 3 goes to state 1, which also goes to state 3 by way of epsilon. So given A, our destination will remain in state 1, 2, 3. For an input of B, state 1 goes to state 2, state 2 goes to state 3, and state 3 goes nowhere. So our destination will be state 2, 3. Now take a close look at our finished product. This is totally functional and this is fine, but there's some automations that we can make. Something that becomes obvious the more you look at it is you realize that some of our states are not actually reachable. State 1 and state 1, 2 do not have any input transitions coming into them, so they cannot be reached. It is safe to remove these states. After this removal, our DFA will look something like this. So that is the process from converting an NFA to a DFA, and by doing so, we have proved the equality between the 2 types of automata. I'm going to make a short follow-up video explaining how we can prove the regular language operations much easier using non-deterministic finite automata. See you there.